Welcome to lesson 20. In this lesson we're going to be looking at process capability. So the overview of this lesson is what is process capability, how do you measure process capability, and then looking at some process capability studies. If we look here at our graph, we've got our normal operating range, we've our proven acceptable range, our PAR, and our edge of failure. Process capability is the ability to do a particular work without producing or producing the least amount of defects possible. Process capability analysis helps us to determine the ability to manufacture product within the tolerance limits and the engineering values. Process capability is a measurable property of a process to meet a specification, and it's expressed as a process capability index, so you'll see it referenced as CPK or CP. The capability index tells us how robust the process is and the likelihood of consistently producing product within specification, so it's ideal information to support a process validation. When you're measuring your process capability, the first thing you need to do is identify, well, what are your key quality parameters? They might be things like your tubing diameter, they might be your assay results, they might be the hardness of your tablet, they might be the water content of your process, it might be your length of drying, it might be your length of your product, it might be your length of your process. You need to collect data, at least 60 values to be statistically significant, and you want to go to one significant digit more than the specification. So if your specification is plus or minus 0.1, you want to go to plus or minus 0.01. So your normal distribution looks something like this, your Gaussian curve, which you would be familiar with seeing. You need to present your information in a graphical format, and you should see something like this then as a result. This is an example of a normal distribution showing the data that was collected during a production run. So you'll see you have a smaller number of measures at the outer limits of your specification or your curve, and your mean is 50. So most of your product is fitting into the 50 range. The x-axis is the length of the item in this example, and the y-axis is the number of items or the fraction of total with the various lengths. So for example, if you have 30 items out of a total of 3,000 items measured, had a length of 30.4, you would expect to see a coordinate of 30.4 to 0.01, and that would be on your distribution curve here. To recap, the normal distribution curve, the Gaussian curve, which you would be typically used to seeing, in this center space, you would expect to see 68% of your data falling. In between the second two sets of lines, you've got your 95% of your data, and out to the edge of failure then you've got 99.7% of your data occurring. We have a lower specification limit. Down along here, we've got our upper specification limit. So that is set by our specifications, by our regulations, by our process, by our validation team, by our equipment. When we do our calculation for our CP, if our CP is less than 1, the Six Sigma process spread is greater than the tolerance. So you see quite an amount of our process is outside of our upper and our lower specification limits. If our CP is equal to 1, the Six Sigma process spread is equal to the tolerance if the process is perfectly centered. So if you've got your perfectly centered Gaussian curve, then you're going to be within your margins here. You're just on the outside of it. So 0.3% of your output will be defective. So it's quite a low level of rejects. If your CP is greater than 1, your Six Sigma process will fit inside your tolerance of your upper and your lower specifications, and there'll be room to spare. So that's the ideal scenario. Therefore, the process is capable of producing few, if any, defects if it is centered. So that's the ideal scenario that you want. So you're looking for a CP of greater than 1. Your mean and your standard deviation. To calculate the process capability, we first need to calculate the mean and the standard deviation of the data. So you'll remember how you do that, and it's easy to do it with Excel or through calculator. What is the significance of the mean and the standard deviation when you're looking at a normal curve? Well, your mean is telling you what's at the center of your curve here, and your standard deviation is telling you the width of your curve. So if we take our Gaussian curve here, we've got our lower specification limit, LSL, and our upper specification limit. They are the upper and the lower specification limits for the length in this particular example that we are looking at here. This is our length, and this is our frequency of occurrence of your length in fractions. So CP and CPK. So CP is equal to your upper specification limit minus your lower specification limit divided by 6 times your standard deviation. CPL is equal to your mean, which you've calculated from your data, minus your lower specification limit divided by 3 times your standard deviation. And CPU, your upper limit, is your upper specification limit minus your mean divided by 3 times your standard deviation. CPK is the minimum value that you get when you calculate your process upper limit and your process lower limit, process capability limits. It is the minimum of the two processes that you have calculated out. So the difference between your CPK and your CP is that your CPK takes into account your mean. We'll just go through an example to explain it in better detail. So if we have a process and our specifications for the length of the item in this process are 16 to 83 millimeters, according to the graph on the slide. So our lower specification limit is 16, our upper specification limit is 83. We've calculated our mean to be 50 millimeters in this example, and we've calculated our standard deviation to be 10 millimeters in our example. So what we want to do is calculate our CP and our CPK for this process using the mean and the standard deviations that we have come up with here. So we want to see that our CP and our CPK is greater than 1.33, and that will demonstrate that our process is very robust and it minimizes the likelihood of poor product being manufactured. So that gives us a CPK of greater than 1, which is a good result. Okay, so to do our calculation here, so to calculate our CP, so we take our upper specification limit minus our lower specification limit, so that is 83 is our upper specification limit minus our lower specification limit is 16 divided by 6 times our standard deviation, which is 6 times 10. So that would give us a result of 1.12. So that's greater than 1. So that's a good result. Our CPL is our mean minus our lower specification limit divided by 3 times your standard deviation. So in practice that would give us 50, which is our mean, minus 16.0, which is our lower specification limit down here, divided by 3 times our standard deviation, which is 10, which gives us a result of 1.13. Our CPU, so our upper limit, is our upper limit, which is 83, minus our mean, which is 50, divided by 3 times our standard deviation, which is 3 times 10, and that gives us a result of 1.10. So our CPK is taking the minimum of these results. So the worst case scenario, so our worst case scenario is our CPU, so that's a 1.10. That is our CPK for this particular process. So it's greater than 1, which is good, and we should be happy. We'd be relatively happy with that. So most of our process should be within the upper and the lower limits. We shouldn't have very few defects. So this just demonstrates here our lower limits and our upper limits. So we've got good high capability here. Our Gaussian curve is right inside of this, so our CPK would be greater than 1. And here it is also, but you can see it's slightly skewed to this side, but it's still within our upper and our lower limits. So it's skewed slightly towards the lower spec, so our mean will be lower than if it was centered. Here we've got bad capability or low capability. It's a bad curve because it's quite flat, so it's well outside, our margins are well outside of our limits, our specification limits here. And then this one here is also not capable because even though we have a nice tight Gaussian curve, we're not centered in the middle of our limits. We're outside of our upper specifications, so we're going to be expecting to see quite a large number of defects from this process also. So good capability, our curve is inside of our limits. Bad, it's outside of our limits regardless of the shape. Process variation. The causes of process variation are due to many controlled and uncontrolled events, and the uncontrolled events are due to natural variation that we would expect in our machines. One of the outputs of our OQ and our PQ is the development of attributes for continuously monitoring and for maintenance of our process. Process and product data should be analysed to identify any variation due to controllable causes, and depending on the nature of the process and its sensitivity, controllable causes of variation may include things like temperature and humidity. So temperature and humidity is very important for manufacturing tablets, but it's critically important for things like sterilization. Variations in electrical supply can impact a product depending on how robust your process is, how much material you're going to lose having startups, and how well your equipment is able to deal with shutdowns. It can also have a major impact on sterilization processes. The vibration of the equipment could cause a lot of issues as well if it's not within the process capability. Environmental contaminants, so issues around your air pressures, your particulates in your area, things like that. The light in the area can cause process variation. Human factors is always an issue for any process. You can have lots of human errors. You need to minimize your risk of human errors by putting good documentation in place, good standard operating procedures, good supervision, and good training to make sure that you're minimizing any of those effects as much as you can possibly do. Variability of materials then, so your starting materials could be subjected to change control procedures after the process is validated. That should take into account any changes that might affect your process capabilities. Wear and tear of equipment. Obviously, over time, your equipment may not work as well as it did from day one, so it may be necessary to revalidate your equipment to make sure that it is still functioning properly. And that's where your preventative and your maintenance calibration schedules would come into place as well. They would be monitoring wear and tear to make sure that it's within the acceptable ranges. We need to try and put in appropriate measures to try and eliminate controllable causes of variation wherever we can. If we can eliminate them and reduce variation, it makes the process more consistent, and that will result in a higher degree of assurance that your product will meet specifications and that you will have few failures or rejects. Process capability studies are an ideal way of measuring processes where you've got plenty of measurements possible. Drug products, things you would be measuring would be your tablet hardness, your tablet strength, your granulate size, or your liquid viscosity. Medical devices, you might be measuring things like the length, the width, the height, the thickness, the strength, or the toughness, etc. These measures can give you great information about how capable your process is, and you can make modifications then on that basis to try and make your process more robust prior to starting your process validation. In order to get good data from capability studies, you have to have a normal distribution. It also assumes that the system is in control, so it's very important to graph the data to confirm this. So over to you. Some questions you might like to answer. What is process capability? By what symbol is it characterized? What does a good in-control curve look like? What is the minimum number of points you need to graph for your curve? Thank you very much for your time and attention. We'll see you for the next lesson.